We will simulate numbers in R for the different distributions which we've learned. We remember the tick diameter variable which we created in the previous lesson. We are going to create something similar, although not exactly the same, but we'll generate 10 diameters. To do this, we will use the rnum function. If we click within the parentheses, we press tab, we'll see different arguments, 3 to be specific, and clicking on 1 will insert that automatically. But that's not what I want us to get from this. So I'm going to delete this, then press tab again. And here, on hovering over this argument, we'll see their definition and expected values that we are supposed to insert in them. For n, it's the number of observation, and the length should be more than 1. While mean is what? Vector of means. And SD is what? Vector of standard deviation. So that means that we need a standard deviation and we need a mean to use this function. Now we can take the average of tick diameter, which we have here, and that's 35.57. We can also take the standard deviation of tick diameter. With this new information, we can simulate another distribution that is close to tick diameter. And to do that, we'll pass the value n. N is equals to 10. That's the length of tick diameter, or the number of observation. So n is equal to 10. Mean is equal to 35.57, and the standard deviation is equal to 11.32598. On running this, we have these figures, and if we compare with what we have for tick diameter, we should see that it's different. But now I'm just going to check the mean of this directly, and we see that it's 3.17. And if I check the mean again, you see it's different this time, and that's because of the standard deviation. It influences how the distributions are. On checking again, it's still going to change, 34.18. What does this imply? It means that our values are always changing when we try to simulate using rnum or number generating functions. Now look at the value that we have here. I'm clicking this again, we have something different. This will make me introduce you to a new function which will be very important for this lesson and in all lessons when you simulate number and when you want other people to replicate the results or reproduce the result of your research, and that's called the set.seed. And what set.seed takes as its input is any number of your choice, but I'll stick to 1 to 3. And what set.seed does is it takes a snapshot of the random figure that you generate. Now I've run set.seed. Now I'm running rnum. We have this. Now I'm going to run rnum again. You see that it changes. On running set.seed and running rnum again, we should have exactly this value which we have. So that's what set.seed does. It captures your number and it makes it fixed so that others can replicate what you've done. Another thing to do is to write this in a short form. Write 10, mean of 5.57 and SD of 11.32598. And yes, we'll also have a result. What we've done in this case is called the positional argument. And what positional argument means that since we know the argument that we should use the keyword, that's n, mean, and SD. Since we know the keyword and we know their position in the function, if we check args, then rnum. Args will show us the different arguments. And we have mean, SD, then n. So since we know their positions, we can as well just put the values that I want to pass in. I'm going to assign this to tick diameter 2. Well, I will run set.seed, then run this again. And if we check the result, it should be as the previous one, which is this. Exactly. Now for uniform distribution, we use the RUnif. As I said, it's quite intuitive. And with uniform, we expect the values to be produced to be almost equal, if not equal. They are supposed to be equally distributed. An example is a die of from 1 to 6. So for this, I would generate 100 numbers with a minimum of 0 and a maximum with a minimum of 1 and a maximum of 6. And for this, we have these numbers here. Why this does not produces what we expect, like integers 1 to 6, like in a die. Uniform distributions are either discrete or continuous, and here we have a continuous variable, hence the reason for the decimal point. Or if you really want to get them in whole numbers, you can as well wrap them around round, and we see this. But this is not the right way to produce die. This is just to generate uniform numbers. For binomial distribution, which is distribution for event or non-event, true or false, head or tails, we we use the R binom, and of course you can press the tab to see the argument, and the argument is quite straightforward. N is the number that you want to generate, and size, it means the size of the trial. Now I'll take more time explaining this. Now the size of this trial is 1, then the probability, we'll say, is 0.5.
Let's take a coin as an example.
A coin that can produce head or tails as its result equally. That's the probability, 0.5. And we have only one coin. So we want to simulate how many heads we will have and how many tails we will have. And with this,
our coin has been tossed 100 times.
One coin, and for this is tails and this is head. That's what 011 means. What about if we have 2 coins? For 2 coins, what we do is take our function, and now I'm going to set seed again. But now we increase the size to indicate 2 coins. I'll set seed so we get exactly the same figure, and this is for 2 coins. What the result here implies is that for the first trial, only 1 coin is having head. For the second trial, both coins are head. For the 38th trial, both coins are tail. So running this again, we'll see that we have exactly the same result. Once you set your seed, you should get this result too. What about if you have more coins, like 5 coins, 10 coins, 100 coins? You can as well just set it in the size. And here we have 3, 2, 4 with 5 here, showing that everything that appeared here, they are heads, and 4 heads here and 3 heads here. So that's what this implies. We've also seen situation of coins that are not fair. And for coins that are not fair, the way we simulate that is we put in our number, of course. The size, we say, is 1. But now the probability of getting head would reduce. Of course, we can increase it.
As long as it's not equal, it's no longer fair.
So we'll say the probability is 0.1. And for this, we'll see that we have more zeros than 1. And that's because it's no longer a fair coin. But if we increase this to, of course, I should set the seed here. So I should just run this set.seed here, so we get the same thing. So if we run this and we increase the probability of having head to 0.8, we'll see that more heads, which is 1, would appear than tails. And that's what we have here. We can as well check the sum to see how many are heads and how many are tails. Set seed, then run this, 82. That's 82 heads. And there we go. Now for the last one, Poisson distributions. Poisson distributions, as we covered in the last lesson, is for count data and events happening within a period of time. And for that, we use the outpoise. And for outpoise, what you need is n. That's the number of events.
And lambda, which is the average time an event happens between an interval or a period of time. For example, let's say the number of emails you get within 1 hour is 7. Given this, we can check the number of emails we'll have in 1 hour for 100 events.
You see, you have 8, 6, 12, and like that. So that's what the Poisson distribution does. Now, a good way to understand what we've done here is to visualize the distribution and how they look like. And for that, I'll create a new section from, let's see, code. I have add section here, start section. But I prefer to use the shortcuts, Ctrl Shift and R. Ctrl Shift R. Then I'll say plotting distribution. For the first one, the R num, set this to 1 to 3, and I'll take this, simply copy this and drop it here. Oh yeah, and I'll plot it. I'll simply wrap this in plot, and this is what we have. But this is likely not what we expect. What we expect is density, to see the curve around it, and for that we use density. We wrap that around this. Do not bother about this for now. We're going to cover this in future classes. And on running enter, we can see the density of the distribution with the mean and the standard deviation here. And we see that, okay, yes, this is a normal distribution. Also, we can plot our tick diameter. Remember the first variable, tick diameter. And now we have this also. If we compare the plots, this and this, we'll see that they are both normal distribution, with the difference just being how they are skewed. But for uniform distribution, we have 100, 1, and 6. I want to plot this. For this, we can check the histogram to check the distribution. And here we go. This is the histogram. Uniform distributions, they're supposed to be equal all through, but it seems they are unequal now. The way to see that indeed that this is still equal, to increase the number of observations which we have. The more we increase the number of observations, the more they level out. So we have 1000 now, and we see that it levels out. Once we increase it again, 10,000, it's continuing to level out, and now it's 10 million. I will see that, yeah, it's almost the same all through. It's uniform, and that's the uniform distribution. So for the binomial is, if you recall, is yes or no, and the probability of this is 0.5. Can plot this, but we need to include the density. So we see the distribution, and this is what we have for the binomial. We see that it's bimodal here, with one being for 0 and the other being for 1, showing that the points are usually centered around 0s and 1, exactly like that. Alternatively, you could check the histogram and you see is we have 2 numbers only, 0 and 1, and the number of times that they occur. And since it's 0.5 probability of both occurring, they should be equal. But if we increase this to 0.9, you should see that one is more than the other. So this is quite straightforward and intuitive. Next is for the Poisson distribution, and that we have 100 events, we have lambda, we have 7.5 here, 7.6, and we plot it. On plotting this, we have this, no, it should include the density, and here we have it. So in this lesson, we've covered the distribution, how to simulate numbers for the different kind of distribution. What we did not cover here include how to generate their individual distribution function, their quantize, and their density. We only covered how to generate random deviates or random numbers from them. See you in the next lesson.